Periodic trends are found by looking at the periodic table. The first thing that we have to look at is the way elements in the periodic table are organized. So the first thing is, if we go down a column in the periodic table, we're actually looking at the group. So this would be group 1, or depending on the version of the periodic table you're using, group 1A. Likewise, there'll be group 2, 2A. The transition metals go from 3 to 12, or 3B. And then we resume back to the A groups from 3A, 4A, 5A, or 13 through 18, 3A to 8A, if you're looking at that version of the periodic table. So different versions have different group numbers. Usually, the first two groups of the periodic table, group 1 would be the alkaline metals, group 2 would be the alkaline earth metals. These have an S1 and S2 outer valence shell electron configuration. As you go across the periodic table, you're looking at the period. So period is going from left to right, and they are basically organized by increasing a principal quantum number. So this would be period 1, this would be period 2, period 3 is shown below it, and then highlighted here would be period 4. We also have the p block elements. Those are from 3A to 8A. These are where the electrons that go in, and then we also have the d block elements. These have 10 valence electrons. The electrons go into the d orbital. These have multivalent oxidation states that vary from +2 to +5. For example, vanadium has oxidation states that vary from +2 to +5. Iron can be +2 or +3. These are electrons that are released from the d shell. These are generally called transition metals. And finally, we have the F block. So if we go from 55, 56, 57, we have a slight detour, and then move from 58 to 71, we're actually filling in the F electrons here. Finally, we have the last and final group that we want to talk about in the periodic table, and that's the noble gases. The noble gases are actually completely inert. They have a full s orbital and a full p orbital, so all their valence electrons are housed in s and p orbitals. So in that regards, the noble gases are inert and tend to be unreactive. The periodic trends that we'll look at are effective nuclear shielding, the atomic radius, ionic radius, electronegativity, electron affinity, and then finally diagonal relationships. Some of these have a very clear trend. Others, such as ionic radius and electron affinity, do not really have a clear trend across a period and down a group in the periodic table. First, let's look at effective nuclear charge. This is the charge that's experienced by an electron with regards to its attraction to the protons. The charge actually increases, also known as effective nuclear charge. That's what the ZF is. That increases across a period in the periodic table, and it increases down a group in the periodic table. So let's take a look and see what's happening. First, let's define effective nuclear charge. It's the positive charge an electron experiences due to the shielding effect caused by core electrons. So if you take a look at the leftmost diagram, you have two electrons, and this electron is experiencing the full charge of the protons in the nucleus. And the electron housed in that blue square is also experiencing the full charge of the protons that are housed in the nucleus. Now remember, as you go down a group in the periodic table, you're increasing the number of protons. Likewise, as you are going across a period in the periodic table, you're increasing the number of protons by 1, and you're also increasing the number of electrons by 1. But as you increase the number of electrons, you're also causing mutual repulsion amongst those valence electrons, as those electrons and the core electrons, as those electrons get added to the s, p, and d shell. Look at the situation on the right. In this case, the electrons are traveling across their orbitals, and you see the electron in the red is on the outside, and the electron on the blue is more towards attracted towards the protons housed in the nucleus. So this electron that's in the blue, we say, is shielding from the full effect of the protons in the nucleus, is shielding that red electron, or that electron in the red square. So the red electron is shielded, the blue electron is not as shielded. In a similar vein, the valence electrons or the outer electrons are actually shielded, and the core electrons are really experiencing the full effect of the attraction towards the protons. So remember, this black dot would represent the nucleus that houses protons, which are positively charged, as well as neutrons, which are neutrally charged. They don't play a role in the effective nuclear charge. So these electrons that are in the core are facing a tighter pull or attraction to the nucleus. These valencer electrons are feeling less of a pull towards the nucleus that has the protons, and they're being repulsed by the other electrons as we go down a group or across a period. Now, if we introduce a third electron here, that electron is also going to be attracted to the nucleus, but it's also going to be repelled by these two electrons. And so these two electrons are going to shield this electron here. Likewise, we add a fourth electron. These three electrons now are going to shield this fourth electron. We add a fifth electron here. This fifth electron that we add is going to experience shielding from all the other electrons. So as we increase the electrons, more electrons become valence, and more of the electrons become shielded. So the effective nuclear charge increases for those electrons as we continue to add them both across a period and down a group in the periodic table. So the effective nuclear charge, in essence, is related to the atomic radius. So here we're looking at sodium, magnesium, aluminum, and silicon. The only thing you're increasing is the valence electrons in the s orbital and the p orbital when you're talking about aluminum and silicon. So as you increase the number of electrons, they go into the outer or valence shells, and they experience more and more and more of that effect, of that shielding. Now, as a result of that, what happens is that your radius actually decreases as you go across a period, because as you add more and more electrons across a period, more of those electrons are going to the p shell and the p orbital, and that's more tightly knit or tightly attracted to the nucleus. Now you have to remember the shape of the p orbital. The p orbital is a dumbbell shape, and right at the center of the dumbbell are nodes. The d orbital also has nodes, which are regions of electron density where there is no electron density to be found. So the s orbital really is the orbital where the electron density is more spherical in distribution. So as you're adding electrons to the s orbital, there are more outer electrons, and there's more probability of finding them. As you add electrons to the p orbital, which you do as you go across the periodic table, you're adding it to orbitals that have zero densities, and so they tend to be smaller because the electrons have less of a place to go to. Second trend that we want to look at is the atomic radius. The atomic radius decreases across a period from left to right, and it increases down a group from up to down. So the definition of the atomic radius, or the radii, is the distance of the center of the nucleus to the outer electrons. It's akin to drawing a circle, and the radius of that circle would be your atomic radius. Now, if you look at the trend here, the atomic radius increases from right to left, or in other words, decreases from left to right. And if you want to look at the trend across a period, you have to look at the electrons. You notice here lithium and sodium and potassium, they have outer valence electrons. In fact, those electrons that are in the valence outer shells are ready to be given away. As you move across a period, you're adding electrons to the p orbital. The p orbital tends to be more closely knit or have a tighter attraction to the nucleus. You also have nodes in the p orbital, regions of zero electron density in the orbital three-dimensional structure, and that also makes it less likely that you'll find an electron in an outer area, but more closely aligned or more closely attracted to the nucleus. Now, why does atomic radius increase down a group in the periodic table? The answer is more simple here. You're increasing principal quantum number. So the principal quantum number for H is 1, for lithium is 2. Sodium is 3, so the energy levels increase, so those electrons are going to energy levels and energy orbitals that are farther and farther away from the nucleus. The principal quantum number for potassium is going to be 4, rubidium is going to be 5, and cesium is going to be 6. The same trend kind of holds true for the ionic radius. We define the ionic radius as a radius of an ion, that could be a cation or anion, to that of an atom, forming an ionic bond. So if you have an ionic interaction, which is a complete electron transfer, the cation will lose its electron, the anion will gain its electron. Here you have an ionic interaction, and the net result is the donor loses electron density, becomes positively charged. The gainer gains that electron density and becomes larger in its ionic radius. So the trend of ionic radius really works for S and P valence electrons, not so much for the D block as you see here. If you look at the s orbital, let's begin by going from left to right. You are losing 1 electron in lithium, you lose 2 electrons in beryllium, and then you skip over to the p block. Nitrogen gains 3 electrons, oxygen gains 2 electrons, fluorine gains 1 electron. You see the ionic radius tends to decrease, but that trend is not really substantial. So there really is no trend if you go from left to right, especially when you look at the D block. So here at the D block, or your transition metals, you're essentially losing electrons at the d orbital, whether it's 3d, 4d, or 5d, and those are the same energy level electrons. So nothing really happens when you lose electrons from a d orbital in terms of size, because there's 10 electrons in the d orbital. So not much happens in terms of size, and you can actually see that the variation, if any, is very little. And as you go down a group in the periodic table, you tend to see an increase in ionic radius. That's because you're increasing in principal quantum number. So you're losing electrons from higher and higher energy shells. So you still maintain that relatively large ionic radius. Obviously, for anions in the p block, as you gain 2 electrons or gain 3 electrons, the ionic radius increases because you're gaining electrons, you're gaining those electron densities and electron clouds. So really the trends occurs for ionic radii if you're looking at S and P valence electrons. So down a group, the P electrons increase in size, going from 171 to 70. For nitrogen and oxygen, you can see the increase in size as shown by the bold green letters. And the same thing is true for the group 1 alkaline and group 2 alkaline earth metals. As you lose electrons, you gain in size, though again that's because what you're losing is outer electron orbitals. So even though the lithium and sodium are deficient in size relative to the neutral atom alone, you're losing the valence electron shells, those electron shells that are on the outer and ready to give. So there really is no trend for the ionic radii unless you want to really talk about going down a group for S and P electrons and across a period for the S and P electrons, though the trend is really not as great as you would be expecting. So in other words, if we are to compare a trend in ionic radii, we really have to look at groups between groups and between periods. In other words, it's really useless to compare an element group 2, its ionic radius, with an element from group 6. Also, it would be irrelevant to compare an ionic radius from an element in period 2 with an element from period 6. So we can't really compare across groups, and we can't really compare across periods for an ionic radius. Second trend that we want to talk about is the ionization energy. The ionization energy is defined as the energy required to strip an electron in the gaseous state, and that ionization energy increases as you go from left to right in the periodic table or across a period, and it also increases as you go up to down in the periodic table or as we go down a group in the periodic table. So in order to define ionization energy, we have to look at the electronegativity. So here we have 2 covalent compounds. One is carbon tetrachloride, CHCl3, that's methylene chloride or methylene chloride. This is carbon tetrachloride. You notice here that this Cl actually pulls its electron density towards the Cl and gives that Cl a partial negative charge. These Cl's here also pull electron density towards themselves. So this is a covalent bond, but I would say that it's a covalent bond that is an unequal sharing. Because chlorine is an electronegative element, it's pulling electron density upwards. Likewise, chlorines here, these three substituents are pulling electron density towards themselves. So within carbon tetrachloride, CCl4, you have regions that are partially negative and regions that are partially. The pull from this chlorine atom, that vector, cancels out the vector from these three Cl atoms that are pulling in the opposite way. So you have what's known as no net dipole moment. So this molecule is really neutral because the pull from the Cl upwards is canceled by the pull of these three Cl's downwards. And that's talking about this in terms of vectors. Now you contrast that with a polar molecule. Polar molecule has a net dipole moment. So you have these three Cl's here. This Cl in this covalent bond is pulling electron density towards it, making it partial negative. This Cl is pulling electron density towards that atom, making it partially negative. This Cl in the CCl bond is pulling electron density towards it, making it partially negative, making this carbon partially positive. But that hydrogen is not really doing much pull because hydrogen does not have electronegativity. Usually the most electronegative elements are the fluorines and the oxygens and the nitrogens and the iodines and the sulfurs, the nitrogens. These are the p block elements going from left to right in the periodic table. So the net effect is that this molecule has a net dipole moment pointing down. This molecule here on the left has no net dipole moment. So since this has a net dipole moment, the Cl is pulling electron density more towards itself. Now, looking at the ionization energy with regards to atomic number, here is the general trend. So if we're going from hydrogen to helium, we're talking about period 1. We're talking from lithium to neon, that's period 2. We're filling the N equals 2 shell. From sodium to argon, we fill period 3, or going to period 3. From potassium to krypton, that's period 4. Rubidium to xenon is period 5. And cesium all the way to radon is period 6. Notice for the most part, as we grow across the period, the energy increases. Now you do see some trends that vary, and that's actually shown in the highlighted regions, highlighted in yellow. We do see some dips. So again, this is a trend, and there's some diversions in the trend. So let's take a look at one diversion in the trend here. Normally, looking at period 2, from lithium to neon, going across this period left to right, the ionization energy really increases, but we do see some dips. So the trend is not 100% accurate. We want to focus on one of these outliers. One of them would be nitrogen and oxygen. So looking at the electron configuration of nitrogen versus oxygen. So looking at the electron configuration of nitrogen on the left, oxygen on the right. The electron configuration of nitrogen is 1s2, 2s2, 2p3. The ionization energy is the energy required to remove that electron in the gaseous state, so we remove that one electron. And the net result is it takes 1400 kilojoules per mole just to remove that one electron in red. If we don't, we have an electron configuration of 2s2, 2p3. Now contrast that with removing an electron here for oxygen, which has an electron configuration of 1s2, 2s2, 2p4. Now, to make that electron disappear, you need an energy of 1340 kilojoules per mole, so about 60 kilojoules per mole less, and that's a violation of our trend going from left to right in the periodic table. We're actually going down in ionization energy and going from nitrogen versus oxygen. Here's oxygen's electron configuration without removal of that electron. So the first ionization energy actually is greater for nitrogen than it is for oxygen. And the reasoning behind this outlier simply has to do with the fact that it's just more energetically stable to go from a state where all the p orbitals are partially filled to a state that is shown here where it's completely half filled. Having a completely half-filled 2p subshell is much, much more energetically favorable, so it takes less energy to remove that fourth electron in oxygen than it does to remove that third electron in nitrogen, simply because of the fact that removing this electron puts it into a little bit of a less favorable state. It's much, much better that you're completely half-filled than to have something that's empty. By the way, there's also second ionization energy and third ionization energy that's required to strip the second and third electrons from the gaseous state. So opposite to this is electron affinity or electroaffinity, and that is the affinity of an electron towards an element. So the more electronegative the element is, such as fluorine and oxygen, the more likely it will gain an electron. So here, the more positive value you get, the more affinity the element has towards an electron. So notice here, fluorine, actually one of the most electronegative elements in the periodic table, when it gains an electron in the gaseous state, it releases 328 kilojoules of per mole to the surroundings. That negative sign means it's releasing energy to the surroundings. That's a lot of energy, and that implies a very high affinity of electron to fluorine. So flipping that sign, that means the electron affinity of fluorine towards one electron in the gaseous state is 328 kilojoules per mole. So the higher the number, the more positive the number this is, the more electron affinity that is, also the more electronegative that element is. Looking at oxygen, oxygen is also electronegative. So gaining an electron for oxygen results in a release of 141 kilojoules of mole to the surroundings. That minus sign means release of energy to the surroundings. So the electron affinity is just flipping the sign of that to plus 141 kilojoules per mole. We would imagine the group 1 and group 2, alkaline metals and alkaline earth metals, they would not have a positive electron affinity. They would have, in fact, a negative electron affinity. They hate electrons. They want to give away electrons. They're not electronegative. So there's really no trend in the periodic table for electron affinity, other than you should know the more electronegative the element is, such as the halogens, such as oxygen and nitrogen, those p-block elements, more likely they will have a higher affinity towards attracting electrons. The periodic table also has what's known as a diagonal relationship. So if you look at group 1A and 2A, you want to skip the D-block elements and look at group 3A and 4A, you notice that the diagonal elements have a lot of the same properties. So for example, boron and silicon located diagonally from 3A to 4A, group 3A to group 4A, they're both semiconductors. They are both metalloids, which means that they have both properties of metals and nonmetals. If you look at 1A and diagonal to that, magnesium in 2A, and beryllium and diagonal to that from 2A to 3A, housing aluminum, they're diagonal to one another. They also have a lot of the same properties. For example, they react with halogens and they form acidic oxides. So one of the relationships that happens because of this diagonal relationship has to do with trends in the periodic table. So if you go down a group in the periodic table, you're experiencing decreasing electronegativity, increasing atomic radius, less covalent character, and more ionic character. That's going up and down or down a group. If you're going across a period in the periodic table, you're actually experiencing increasing electronegativity, decreasing atomic radii, more covalent character, and less ionic character. So the properties down a group cancel with the properties across a period, and as a net result, elements that are diagonal to one another essentially have the same properties because the decreasing electronegativity down a group cancels with the increasing electronegativity across a period. The increasing atomic radius down a group cancels out with the decreasing atomic radius across a period, and on. The same trends occur for covalent character and ionic character as well. So elements from 1A to 4A that are diagonal to one another have the same properties.